Hi students, in this video we're going to cover the basics of trigonometric functions. We're going to split the trigonometry into two videos. The first part is going to cover the 6 trigonometric functions and basic identities, and the second video will cover the inverse trig functions and how we use them to do more trigonometry. So an expectation for both sections is you have a basic knowledge of the unit circle and we understand right triangle trigonometry. Okay, so first let's get started with the graphs of the trigonometric functions. In this diagram, we have the graph of sine theta and its reciprocal function cosecant theta. So the sine function is periodic every 2 pi, and we know from being on the unit circle that we can find the sine and cosines of any angle. So if we have, we'll just draw our version of the unit circle. So on the unit circle, we know that sine is a y value. So remember on the unit circle, we have a point that is cosine theta and the y coordinate is sine theta. So at this point, 1, 0, that's going to tell us that the sine value is 0. We know our angle theta is equal to 0 degrees or 0 radians. So if we take a trip around a unit circle, let's do this in a different color. We'll go yellow. So if we move up to 90 degrees, so we end up at the point 0, 1, and that's going to tell us that the cosine of theta is 0 and the sine of theta is 1. And we know at pi over 2 or 90 degrees, the sine of theta is equal to 1 for, again, pi over 2 or 90 degrees. So we can see on the unit circle that our sine value is always going to be between 1, or if we all travel all the way down, we'll get to the point 0, -1, and this happens when theta is 3 pi over 2 or 270 degrees. And there are many angles that have this value. So we can travel around a unit circle counterclockwise or clockwise as many times as we want, and we can always get a sine value. That's going to make the domain for our sine function all real numbers. We will write this as -infinity to infinity, and we can see this on our graph. We can see that the x continues to go right, and x continues to go left. The range we'll notice is that the highest our sine value can be is 1, and the smallest it can be is -1. So our range is going to be inclusive -1 to 1. And this, again, these are the graphs without any sorts of transformation. We'll talk about the transformations in class. So the fundamental period for the sine function is, so the period is 2 pi, and the fundamental period starts at 0 radians up to 2 pi radians. So this part that we'll highlight in black is the fundamental period for the sine function. So we'll even write that. We'll say the fundamental period is from 0 to 2 pi inclusive. And so now if we look at the cosecant function, cosecant is, so we know cosecant theta is 1 divided by sine theta. So cosecant is going to be undefined everywhere that sine theta is equal to 0. So if we look at our graph, we'll notice that everywhere sine is equal to 0, the cosecant function has an asymptote. So we see at pi, 2 pi, 3 pi, 4 pi, we have asymptotes. So that's going to tell us that our domain is theta cannot equal any multiple of pi. K is any integer. So we can have any multiple of pi. Now, if we look at our range, it seems like cosecant is at least 1 and continues up, or it is at least at most -1 and continues downward. So that's going to make our range -infinity to -1 union 1 to infinity. And it's not possible to get a value between -1 and +1. The period, we'll notice that if we look at, we get, we'll say like an up graph and we get a down graph, and that repeats every 2 pi. So the fundamental period, just like the sine function, is from 0 to 2 pi. And so we'll just say the fundamental period is also the same thing for that function. If we move to the graphs of cosine and its reciprocal secant, cosine and secant behave exactly like sine and cosecant, except they are shifted backwards 90 degrees. So if we look at the domain for the cosine function, which is in pink or magenta, we'll notice that the graph every 2 pi radians repeats. So we'll start high, go low, go all the way back up to 1, and start over. Now again, if we see this on the unit circle, we'll get this. And so if we draw our circle, we'll see if Mr. Martin did a good enough job. Pretty good. So now here, now we're starting at, so remember again, we get a cosine value for theta as the x and a sine value for theta as the y. So we start at the point 1, 0, and that's why our cosine function starts at 1. So we start at 1, and the x, because it's an x value, we get smaller and smaller until we get to 0. That happens at pi over 2. And then we keep going around and we get to -1. So we start at -1, go all the way backwards to -1. So this is what we've traced so far on the unit circle. This blue part, probably not a good idea since the secant graph is in blue. So this is what we've traced so far in our cosecant graph. And so then cosecant repeats the negative values first. So we go from -1 back to 0. So from -1 back up to 0. And that gets us to 3 pi over 2, or 270 degrees. And then we go from 0 back up to 1. And that takes us from 270 to 360. And then we will repeat all over again, starting at 2 pi. So just like sine, the domain is all real numbers because we can do the cosine of any angle. The range, just like sine, is from -1 to +1, and the period is 2 pi. The fundamental period is just like sine, from 0 to 2 pi. For secant, very similar to cosecant, it has the exact same domain and range. The domain is, well, it doesn't have the same domain and range. It has the same restriction. Secant is 1 divided by cosine theta. And so whenever cosine is 0, we're going to have asymptotes for cosecant. And so we'll notice that that happens at pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. So it seems like at the odd multiples of pi over 2 is where secant is undefined. So we're going to say our angle theta cannot be an odd multiple of pi over 2. So this 2k, I'm sorry, hold on. So theta cannot be 2k plus 1, and this is any odd integer. And so if you think about this, the way we get all of the odd integers is you do 2 times an even number and add 1 to it. For instance, 3 is 2 times 1 plus 1. 1 is 2 times 0 plus 1, and so forth. So we have 2k plus 1 pi divided by 2. Theta cannot be any of those values. The range is identical to cosecant, which is from, hold on, we meant to do negative infinity to negative 1 inclusive union 1 to infinity. And again, notice for cosecant, where the cosine graph is, the secant graph is undefined. There is no blue graph that overlaps with the pink or magenta graph. And just like cosecant and sine, secant has the period, it repeats every 2 pi, and the fundamental period is 0 to 2 pi. And so last we have the graph of tangent and this reciprocal function cotangent. Why did I write? All right, hold on. Typo here. Let's fix that. I was copying and pasting and I did not catch this. This should be tangent theta, and this should be cotangent theta. So if we look at our tangent graph, our domain, we can't, so remember tangent is sine theta divided by cosine theta. So it has the same domain as secant. So that's going to tell us that theta can't be any odd multiple of pi over 2. And if we look at our range, well, tangent starts low and starts at negative infinity, goes all the way to positive infinity, and it just keeps doing that. So the range is all real numbers, and the period. So tangent is going to repeat. Like if we start at 0, go all the way up to infinity. We have an asymptote, and then we start at negative infinity and go all the way back up to 0. So these values are going to repeat every pi radians. And though you can't see it, we're going to consider the fundamental period for tangent is from negative pi over 2 to pi over 2. And we'll make this value negative pi over 2. So our fundamental period for tangent is going to be negative pi over 2 exclusive, which is why we have rounded brackets or parentheses. So from negative pi over 2 to pi over 2. Now for cotangent, cotangent is the ratio of cosine theta divided by cosine theta to sine theta. So that's going to mean our domain is theta cannot equal. And so now we're looking at the multiples of pi because that's where sine is equal to 0. So theta can't be any multiple of pi. K is an integer. And just like cotangent, the range is negative infinity to infinity. And the period, just like tangent, is pi. And the fundamental period, we get one complete period of pi if we look at cotangent if we go from not inclusive, exclusive from 0 to pi, exclusive. You can't see it because we have the axis drawn, but there should be an asymptote on the y-axis as well. All right, so those are the bases of the graphs. In calculus, we do not need heavy manipulation of the graphs using transformations, even though in class we will talk about some of them. But just a basic understanding of how the graph should look and their domains is what we generally focus on. All right, so some of the common identities that we should know, the sine of theta is equal to, that's 1 over cosecant theta. Cosine is 1 over secant theta. Excuse me, I don't know what just happened. Cosine theta is 1 over secant theta. Tangent theta is 1 over cotangent theta. Cosecant theta is 1 divided by sine theta. Secant theta is 1 divided by cosine theta. And cotangent theta is equal to 1 over tangent theta. And also for tangent, let's also do tangent theta is sine theta over cosine theta, and cotangent theta is cosine theta divided by sine theta. One of the fundamental identities we use is the sine squared plus cosine squared equals 1 identity. And we get this from the unit circle. So on the unit circle, we know we have this point cosine theta, sine theta, and because we're on the unit circle, we know the radius is 1. So what we know is that the distance from the center to the edge up to the circumference of the circle is 1. Now, if we did the distance formula using the point cosine theta, sine theta, and the point 0, 0, we would know that d equals the square root of cosine theta minus 0 squared plus sine theta minus 0 squared. But we already know that distance is 1. So that's going to tell us that, we'll keep going down here, that the distance is the square root of cosine squared theta plus sine squared theta. We know that distance equals 1. Well, the first thing we can do is just square both sides. So we end up with cosine squared theta plus sine squared theta equals 1. And that's how we obtain this fundamental identity here. It's one of our Pythagorean identities. So to get the other identities, we can divide this given identity of sine squared plus cosine squared equals 1, respectively by sine squared and cosine squared. So let's do that. So one that we'll use is, well, if we take sine squared theta plus cosine squared theta and say that equals 1, and we're going to divide everything in our problem by sine squared. So we divide the first term by sine squared theta, we divide the second term by sine squared theta, and we divide the third term by sine squared theta. And that's going to tell us that, well, sine squared divided by sine squared is 1. So we get 1 plus cosine divided by sine is cotangent. So cosine squared divided by sine squared is cotangent squared theta. And then 1 divided by sine squared theta is going to be cosecant squared theta. This is our second fundamental identity. So we have one key identity, a second key identity. Now our third one is, say we take sine squared theta plus cosine squared theta equals 1 and divide everything by cosine squared this time. So instead, we divide by cosine squared theta, divide by cosine squared theta, and we divide by cosine squared theta. So now we're going to get sine divided by cosine is tangent. So sine squared divided by cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. And 1 divided by cosine squared is secant squared theta. So this is how we derive the other Pythagorean identities by dividing this fundamental identity here by sine squared or by cosine squared. So if you ever forget 2 and 3, just remember that you can divide by sine squared or cosine squared, and that's how we obtain 2 and 3. All right, so next we have some common identities that we use in calculus. Very important is the sine of a double angle and the cosine of a double angle. These other two identities that I'm putting curly braces around are derived from using this identity. So pay careful attention to the ones where we have exclamation marks. The sine of a double angle and the cosine of a double angle are very important. And it should be noted that if we replace theta with any other value, the values of theta change, not the coefficients. So for instance, if we have, say we had the sine of 4 theta. Now technically, using our double angle identity, that's really the sine of 2 times 2 theta. So all that means is that to do the sine of that, that's going to be this, I'm sorry, I messed up. So the sine of 4 theta is going to be 2 sine 2 theta cosine 2 theta. And for this one, for instance, say we did the cosine of 8 theta. Well, that's going to be the same thing as cosine squared 4 theta minus the sine squared of 4 theta. And understanding that we can manipulate the angles this way is going to help us, especially in calculus 2, when we're doing trigonometric substitutions and when we're doing the power reduction formulas for sine and cosine. So, some of this stuff also applies to tangent, but it has slightly different rules. So important here is when we change the value of theta, we're not changing these coefficients like the 2 here, the 1, the 2, or the 1 and the 2. Only the actual angle is going to change. All right, so next we're going to another thing that we do commonly in calculus is manipulate a trig expression to get something far simpler so that we can either derive or integrate it easy. So sine divided by cosine theta, we need to sine theta divided by cosecant theta plus cosine theta divided by secant theta equals 1. We need to prove that. So to prove this, remember for a trigonometric proof, you work with one side of the identity, generally the more complicated side, and make it equal the opposite side. So in this case, we're going to put the 1 in a box, which means that we're not going to change the 1. This is going to be fixed, and we're going to work this side. So we're going to work the left side. So the first thing we can do, and I recommend in general, is if you do not know where to start, turn everything into sine and cosine. So that means that we can turn cosecant and secant into what they represent in terms of sine and or cosine. So in this case, we would get sine theta divided by cosecant is the same as 1 divided by sine theta. And then we'd have plus cosine theta divided by 1 divided by cosine theta, and that equals 1. So next, we know that if we are dividing by the function, we can multiply by its reciprocal. So the reciprocal of 1 over sine theta is sine theta. So we would have sine theta times, you know what, we'll color code this so it actually makes sense. So this is the 1 over, actually just erase it, Mr. Martin. So we said that this was 1 over sine theta, and we'll make this 1 over cosine theta. So now we have sine theta times sine theta. We multiply by the reciprocal, and then that's going to be plus cosine theta, and we multiply by the reciprocal of 1 over cosine theta, which is just cosine theta. And so that's going to give us, so sine theta times sine theta is sine theta, sine squared theta plus cosine squared theta. And we know from our Pythagorean identities that this is 1. So we end up with 1 equals 1. And we can carry this step through. The equals 1 part we said we would never change. And so at some point we end up with 1 equals 1. We'll do some more common identities that we can manipulate for calculus in class as like some group work. And finally, we have solving basic trigonometric equations. So the general rule of thumb is if we have sines and cosines mixed up, we want to replace one of them. So let's look at the identity sine squared theta plus cosine squared theta equals 1. So in this formula, we have a sine term, a cosine term, a sine term, and a 1. So I would say it's very helpful that we have 2 sine terms and 1 cosine term. What that's going to tell me is that we should use this identity to replace cosine in terms of sine. So if we solve this identity for cosine squared, we're going to get cosine squared theta is equal to 1 minus sine squared theta. So we're going to replace cosine squared here with that identity. So we get sine squared theta minus, and in parentheses, we're going to put 1 minus sine squared theta plus sine theta plus 1 equals 0. So if we distribute, we would get sine squared theta minus 1 plus sine squared theta plus sine theta plus 1 equals 0. So now conveniently, the negative 1 and positive 1 add to be 0. So we get 2 sine squared theta plus sine theta equals 0. So what we want to do is, all right, so the first thing that we always do when solving an equation is look for a greatest common factor. In our case, both of these have a sine theta in common. So we can factor out that common factor of sine theta. So that would give us sine theta, and then that's going to be multiplied by 2 times sine theta plus 1 equals 0. So you know what? We'll put an additional restraint and say we're working on the interval 0 to 2 pi, the fundamental period for the sine function. So we're multiplying two things. We have the sine of theta times 2 sine theta plus 1, and that product equals 0. So one of two things is true. Either sine theta equals 0 or 2 sine theta plus 1 equals 0. One of those two things have to be true. If we multiply and get 0, one of the factors must be 0. So if sine theta equals 0, we know that theta is going to equal sine inverse of 0. So if you ever forget where the sine values are, draw yourself a very basic unit circle and go for the angles that you know. So here, between 0 and 2 pi, we know the y value or the sine value is 0 at 0 degrees, which is also 0 radians. And sine is also 0 at 180 degrees, and that's the equivalent of pi radians. And we travel back around a unit circle, we end up at 360 degrees or 2 pi radians. So in this case, theta could be 0, pi, or 2 pi. All of those work. So the next thing is, if we solve this other equation, we get 2 sine theta is equal to -1, and then sine theta is equal to -1 divided by 2. And so theta is equal to sine inverse of -1 divided by 2. And I don't know if you remember, but y being -1/2 is going to be, if we consider this to be 1, -1/2 is right here. So we're looking for the two angles where that is true. And we're on the interval 0 to 2 pi. So now again, we have to know the unit circle for this. So that's going to tell us that theta is in quadrant 3 and theta is in quadrant 4. In quadrant 3, the angle that we want is 180 plus 30 degrees. And so that's going to be 210 degrees, or 7 pi over 6. And the angle that's in quadrant 4, which is 360 degrees minus 30 degrees, and that's 11 pi over 6. So in degrees, that's 210 degrees. In radians, I'm sorry, and then in degrees, 11 pi over 6 is 330 degrees. So if you do not remember how to turn angles from degrees to radians, I would recommend reviewing that. It's something we'll talk about very briefly in class. So next, we have find all solutions to sine 4x equals cosine 2x. So first, remember the identity sine of 2 theta is equal to 2 sine theta cosine theta. So all we have to do is use this sine 4x to manipulate that. So the sine of 4x, remember the sine of a double angle, so sine 4x is the same as sine of 2 times 2x. So we're going to get 2 sine 2x cosine 2x. So our equation, instead of being sine 4x, is going to be 2 sine 2x cosine 2x equals cosine 2x. So now if you're thinking you can divide both sides by cosine 2x, that's not the way we want to work this. We want to subtract, so we get 2 sine 2x cosine 2x minus cosine 2x equals 0. The next thing we can do is factor out the common factor of cosine 2x from both terms. So we get cosine 2x, and left over to be multiplied would be 2 sine 2x minus 1, and that equals 0. So like the same property. So we end up with, and so also, let's also say we're still working on the interval 0 to 2 pi. So we end up with cosine 2x equals 0, which is going to mean that 2x is equal to cosine inverse of 0. So now if we're looking at our unit circle again, we'll draw a little unit circle. So remember, cosine is an x value. So if cosine is 0, that means that we're on the y-axis. That happens at pi over 2, and it happens again at 3 pi over 2. So that means that either 2x equals 3 pi over 2, or 2x equals pi over 2. So we either end up with x equals 3 pi over 4, or x equals pi over 4. So that takes care of the cosine 2x. Done. The other thing that could happen is we end up with sine 2x, 2 sine 2x minus 1 equals 0. We'll put a line too. So we would quickly get 2 sine 2x equals 1. the sine of 2x equals a half. So 2x is equal to sine inverse of 1/2. So now we'll do this in blue. So the same thing. If 1 is up here, consider a half to be like right here. So if we draw an angle on the unit circle, sine is going to be a half twice, and we need to know what those two angles are. Now again, if you know the unit circle, you know the first one is 30 degrees or pi over 6. So 2x equals pi over 6. Or sine is also positive in quadrant 2, and that's going to correspond to the angle 5 pi over 6. So in solving our equation, we divide both sides by 2, x equals pi over 12, or x equals 5 pi over 12. All right, kids, that's going to conclude our video on basic trig. Remember, we did the fundamentals here in class. We'll talk more about solving more complicated trig equations and manipulate some more identities. If you need to, please consult the unit circle and learn it. I will have it in the module for this unit. I won't say you must know the unit circle. It's very handy for solving some problems. All right, see you all in class.